In this lesson, we're going to look at more examples of how to identify types of intermolecular forces in a molecule, and we're also going to discuss some of the properties that are affected by those intermolecular forces. An important thing to remember is that intermolecular forces affect the properties of substances. The mere presence of any intermolecular forces, dispersion, dipole-dipole, hydrogen bonding, ion dipole, or ionic forces, affects the behavior of a substance in a large amount because those intermolecular forces change the interactions that are occurring between those individual molecules. Okay, boiling point is when we go from a liquid to a gas, and boiling point will vary for all substances, and it depends on those intermolecular forces between molecules. So a substance like water, which has very strong intermolecular forces, is going to have a higher boiling point than something like methane, which has very weak intermolecular forces. Because what we're looking at is we're taking a substance that's in the liquid phase where the molecules are very close to one another, and we're having to move them apart from one another. And so we're having to break those attractive forces that are holding those molecules really close together, because in the gas phase, those molecules are very far apart from one another. So let's look at a series of molecules, and we're going to look at the intermolecular forces that happen in each of these molecules and how we can relate that to the boiling point. Now, notice that we're going to look at a series where there's something that's clearly changing from one molecule to the next. If we start having very large molecules with only dispersion forces and very small molecules with dipole-dipole forces, it's much harder to compare them. So everything kind of has to be done in a series of some sort. So let's look at the first molecule here at the top. We see we just have carbons and hydrogens, and we see there are 3 carbons, so we have C3. And if we look at our hydrogens, we'd have 3 hydrogens here, 2 for 5, 6, 7, 8. So we have C3H8. And when we get down to the next molecule, we say we have 1, 2, 3, 4 carbons, and that will actually have 10 hydrogens on it. So we're going to compare these two first, because what we see is that the top 2 molecules just have carbons and hydrogens, and the bottom 2 both have an OH group. And what I know about these 2 molecules at the top is that they are both nonpolar, and therefore the only type of intermolecular forces they will have are dispersion forces. We're not going to have any dipole-dipole because we don't have a polar molecule. We won't have hydrogen bonding because we don't meet that rule. No ion dipolar forces or ionic forces. So just dispersion forces. So the weakest type of intermolecular forces. Now we go to the last 2 molecules, and we see that the molecule is getting bigger. So here we have 1, 2, 3, 4 carbons still. Okay, but we have H, and we also have, so we have 3, 4, 5, 6, 7, 8, 9, 10 hydrogens still, but we also have that O in there that's present in the OH structure. We go down to the last molecule, and we see we have C, we have 1, 2, 3, 4, 5, 6 carbons. Okay, and we're going to have 14 hydrogens and 1 oxygen in there, also present as that OH. And so remember, we have that OH, we have a hydrogen bonded to a fluorine, oxygen, or nitrogen, and it's going to be attracted to a fluorine, oxygen, or nitrogen on a neighboring molecule. So we meet that requirement to have hydrogen bonding. Having this OH group also gives the molecule a little polarity, because remember, hydrogen bonding is just a fancy type of dipole-dipole forces. So these are both polar molecules. We have dispersion forces, because what do we need to have dispersion forces in a molecule? Electrons. If we have electrons, we will have dispersion forces. So everybody has dispersion. These molecules are polar, so we will also have our dipole-dipole forces. And because we meet the requirement for hydrogen bonding, the hydrogen is attached to an oxygen, which will be attracted to the oxygen on another molecule that looks just like this. So we will have our hydrogen bonding. Now, because that hydrogen bonding is present, that's the predominant force in this case, the intermolecular forces are stronger in these latter two molecules than they are in the first two molecules. So we know that these last two will have much higher boiling points than the first two. But we can also distinguish between within each of those pairs, because if we look at the first two that only have dispersion forces, what we see is that one of the molecules is bigger than the other, and if it's a larger molecule, it has more electrons and therefore more dispersion forces. When I look at the latter two, I see they both have an OH group, so the strengths of their hydrogen bonding and dipole-dipole forces will be comparable to one another. But what I can also see is that one of the molecules is bigger. Again, we have 6 carbons versus 4 carbons, so we are going to have more dispersion forces, and so that will make the bottom one have the highest boiling point because it has the strongest total intermolecular forces. Had we had a molecule that had 2 OH groups, then we would have seen that that would have had stronger hydrogen bonding than a molecule with only 1 OH group because it has 2 opportunities for hydrogen bonding. If we had a molecule with just dipole-dipole forces and no hydrogen bonding, its boiling point would have happened somewhere in between the top 2 and the bottom 2 molecules. Again, we have to be looking at molecules that are either comparable size or the trend is going in one direction. So let's look at an example here. Which substance will have the highest boiling point? When I look at my molecules, what I see here is I have in A, I'm going to have hydrogen bonding as my predominant force, which also means I have dipole-dipole forces and dispersion forces. In B, it's a nonpolar molecule, so my predominant and my only force are my dispersion forces. And in the last one, I also have hydrogen bonding, but notice that I have 2 OH groups, so I have hydrogen bonding times 2. There are 2 opportunities for hydrogen bonding. All the molecules are about the same size, so overall the dispersion forces are going to be roughly the same. There'll be slight variations, but approximately the same. What's going to distinguish these molecules will be the hydrogen bonding. So in B there's none, which means it's going to have the lowest boiling point because it's the easiest to separate those molecules because it has the weakest intermolecular forces. Okay, so we'll say weakest intermolecular forces. The one molecule with one source of hydrogen bonding is going to be next because it's still going to have a much higher boiling point than B, but it's going to have hydrogen bonding in one place, so it will have less intermolecular forces than our molecule C, which has 2 sources of hydrogen bonding because we have 2 hydrogens attached to an oxygen, which are going to be attracted to those oxygens on a neighboring molecule. So C will have the highest boiling point. B will have the lowest boiling point.